Hello. So, we are continuing with our series of miniature lecture videos. Today, we're going to look at the math and of chemistry, the numeration, the number theory that we need to get through some of this stuff, including the idea of significant digits or significant figures. So, we'll start going to our PowerPoint. Okay, with that in mind. So, the main system of units we'll use is what we call the SI, or System International units of measurement. It's essentially the standardized units that the world uses in general. It's going to be based on the metric system, but mind you, we have certain what makes it SI has to be like, well, what is the number based off of, and also what is the base number that we use to measure things off of, such that a distance of 1 meter has to be set to a certain length. And so originally, like for example, the meter was set to be there's so many of them within when the essentially the diameter of the Earth. There were like so many of them in there, and so we could standardize it based on that. This many meters fits in the diameter of the Earth. But now I think it's changed to in relation to the speed of light. That the speed of light is so many meters per second, and we can use that constant as a basis for the meter. The same thing we can do. Kilogram is a certain size cube of a metal that this weighs a kilogram, and it's standardized, and we can measure all the other things off of that. Like for example, as we'll learn about later, a mole is a relationship that if we have 1 mole of carbon, weight of carbon 12 weighs exactly 12 grams. And the AMU is standardized, so 1 atom weighs exactly 12 AMUs, 1 atom of carbon. So these are the units, the base units we're going to almost all of the other units will be derived from. Now, mind you, occasionally we will see non-metric units, but we will be given conversion factors to convert between the two. So, the things we'll need to know, we'll need to be able to figure out distance in meters, mass in kilograms, time in seconds, temperatures in Kelvin, quantities in moles. We won't really deal too much with amperes or candelas, but they're just examples of other more unique units. Now, all these will have a base 10 numbering system from the prefix. There is a lot more out there that is not used, but there's just a few of these. So I've underlined the ones that are of specific importance to us that we will see very, very often. The one that's often forgotten is absent. If you do not have a prefix, like just a meter, it is absent, and that's coming from the base unit. So it's 10 to the 0. 10 to the 0 is the same as 1. If I'm going larger, deca, hecta, and kilo make up the first 3 factors. From there, it kind of jumps by factors of 3, and we tend not to try to factor in, calculate, give a prefix for 10,000 or 100,000. But we'll jump to a million with mega. And you've probably heard of the billion, which is giga, or trillion, which is tera. And we could keep going, but once we're getting much higher than that, we're getting into crazy big sizes, and we often don't do that. So desa, going down like decade, is the 10. Centa is in century, is 100. Milla is in millennium, is 1,000. We don't really see the deci, but we do see centimeters all the time. We do see millimeters all the time. Micrometers, jumping down by another 1,000. Micro, we use the Greek letter mu. It's the only one that is a non-English letter. That is the Greek letter mu. But we use that for the scale below. So I can see a centipede or a millipede with a naked eye, but if I want to see a microbe, I need a microscope, so it's smaller than that. Now nano is the next one down. Nanoparticles, we're seeing clumps of atoms together. Even a microscope can't show that, so we need a more powerful thing. And if we keep going, we can go pico, femto, even atto, which is covered up, but we don't usually deal with picometers. Picometers, for example, would be something that we might deal with if we're dealing with individual atoms. Femto, you might see femtoseconds and certain things decaying, or things that go so fast it's almost impossible to measure. But other than that, we don't really go down that small, and we won't in this class. Now, a lot of our units will be derived from our base units. So knowing a formula is useful, but typically a good class will have the formulas given to you. You don't need to memorize all these formulas. However, if I look at the units on my answer, I can almost derive the formula from it. So volume, for example, we don't have an SI unit for volume. Well, we do, but it's not a single unit by itself. It's not actually liters. The SI unit for volume would be meters cubed, because the meter is the SI unit. And meters cubed would be m times m times m, which is 3 distances. In this case, a length times a width times a height. However, as I said, we can convert these into liters. There is an easy conversion we can do to go from meters cubed to liters. Density. We don't often use density, but when we do, it's technically kilograms per meter cubed. Kilograms being the SI unit for mass, and meters cubed the SI unit for volume. From there, we can recognize, the formula for density is mass over volume. Now, we'll often see this as grams per milliliter rather than kilograms per meter cubed, but technically it should be kilograms per meter cubed. Density, remember, is an example of an intrinsic property, one that doesn't depend upon the amount of the substance given. So if you have a larger volume, it's going to weigh more. These are going to be less used, but velocity and acceleration, this is more the purview of physics. But velocity is meters per second. So based on the fact that seconds is time and meters is a distance, velocity is distance over time. Acceleration is meters per second squared. So you could either treat that as a distance over time, or a velocity, which is already meters per second over time. And so that's how we'd get that equation. Now, will we need that equation? No. Force, which is given in the units of newtons, typically, but technically the SI unit is kilograms meters per second squared. When we said meters per second squared was acceleration, kilograms is a mass, a weight, so mass times acceleration is our force. A joule, we will use joules, but the SI unit would be kilograms meters squared per second squared. Looking at our force of kilograms meters per second squared, we've just added in another unit of meters. So a force applied over a distance is our energy. So 1 joule is equal to 1 kilogram meter squared per second squared. And frequency, which we'll see later, which is hertz, often given as an inverse second. 1 hertz is equal to 1 inverse second. 1 inverse second would be 1 over seconds. So our frequency, our nu, is 1 over time. Now, some simple things we need to keep in mind while we're doing this. We need to know how to use our calculator. So we'll be using very big numbers and very small numbers. If we do not know how to use our calculator, we are going to have a hard time of it. When you use Avogadro's number, which is 602 sextillion, 200 pentillion, writing all that down, it's a whole mess. And it's very easy to leave out a zero because most calculators do not put the commas in there. And you miscount something, you're off by factors of tens or hundreds. So we often will use scientific notation. If you don't know scientific notation, this is a review. If you do know it, this will still be a review. Scientific notation, it puts in the form where C times 10 to the power of n, where C is a number with the appropriate significant figures, more on that later, written as a decimal with the number C being between 1 and 10. Greater than 1, but less than 10. And n is the number of places we have to move, the power factor by which we'll move the decimal. Because when we multiply by a factor of 10, we are just moving the decimal either to the left or to the right, depending on the power factor. So a positive power factor moves the decimal to the right. A negative power factor moves it to the left. So 523 is represented as 5.23 times 10 to the second. Tenths, hundredths, thousandths. 26 100,000th. 26 100,000th could be represented as 2.6 times 10 to the negative fourth, because I'm moving the decimal. To get back, I need to move the decimal 4 places to the right, to the left. So it would go 1, 2, 3, 4, and that gets it right back where it needs to be. So when writing this, there's multiple different ways to write these, and I'll show this on my calculator in a minute. When writing scientific notation, your calculator has multiple different ways to do this. Your calculator may contain a button labeled EE. It may contain a button called EXP, or it may contain a 10 to the X. It may have a plus/minus, or it may have a minus button. Not the negative sign, but specifically a minus button. So to generate that, one way to type that is 5.23 EE2. I could also type it as 5.23 times 10 caret 2, but EE is a lot faster. if I want to generate 2.6 times 10 to the negative fourth, I can say 2.6 EE. I put the plus minus sign, negative 4. Now, why we want to do the EE instead of the times 10 to the whatever number is if you forget to put in the proper parentheses, you could multiply when you mean to divide or divide when you mean to multiply. So one way to avoid that is to do the EE button, which on purposely links these two together. But one way to check whether our answer is right is remember these simple mathematical rules. If I have two numbers raised to the same number raised to different exponents, or even the same exponent, if they're the same number and I multiply them together, the answer is going to be the number raised to the sum of those exponents. So if I have 10 to the fourth and 10 to the third, the answer is going to be 10 to the seventh. I know that without having to use my calculator. If I'm division is just treating it like subtraction. I'm subtracting by the divisor. So I know if I have 10 to the ninth and I'm dividing by 10 to the third, I should have a smaller exponent, 10 to the sixth, not a larger one, not 10 to the 12th. I know that, and I can avoid that. If you have an exponent, a power function outside of that, it becomes a multiplication. And if you have a root function, it's the same as division. So let's look at this real quick on my calculator itself. So various different ways. So in this calculator, if I want to type 5.23 times 10 to the second, I can do times 10 caret 2. Oh, I did 2.23. That's fine. But I can also say 2.23 second. Okay, so I'd have to be times second 10 2. Or let's see if there's another way. Or I can do 2.23 and that button. However, this one, because it doesn't have the E, if I was trying to divide 2.23 times 10 to the by 10 times 10 to the second divided by 5.55 10 to the third. So let's do this. And then I'm going to divide that by 5.55 times 10 to the third. If I put the parentheses in there, fix that. What? Calculator just died. 3 divided by 5.550. It's going to be this. However, if I was not careful, 2.23 10 second divided by 5.55 10 third, notice I got a number that's much, much bigger. Because I did this times this, then I divided by 5.55, and then I multiplied the answer, the quotient of that, by the 10 to the third instead of dividing by that 10 to the third. Let's see if I have batteries in this guy. Okay, here we go. So in this calculator, I could do the same thing, 2.23, but now I have a second E. That second double E allows me to type the same thing. Now, because this is E, this is intrinsically going to link these two together. I'm going to link the 10 to the second divided by the 10 to the third. Now, if I do this, notice I get the 0.0401 number. So I'm getting the same number that I should be getting. As opposed to if I did it the old-fashioned way, 10 caret squared divided by 5.55 times 10 caret 3. Oh, I divided by, notice I did 2.23 times 10 divided by 5.55 times 10 caret 3. So, notice the EE made sure I got it right. So, just be careful and understand how your calculator works. If you do not, we are going to have some problems. So we got to double check and under our understanding. Now, the other major thing we need to consider is significant digits or significant figures. The thing we talked about previously when it comes to hypotheses and theories is science tries to be as exact as possible, but there's a lot of things we do not know. And so, when you're reporting values, our goal is to only report what we can reliably know within a certain degree of exactness. So we're always going to try to report only what we know and not report hearsay or inaccurate numbers. You wouldn't want to say, oh yeah, this is spot on, when really there is a wide variation of our answers. So in this case, numbers can fall into two different categories. Exact numbers. Exact numbers are numbers we know without any uncertainty. They're often going to be numbers we have defined. We have previously defined this is that number. Like we can report pi to as many places as we want because of the definition of what pi is. We can report 1 meter is equal to 100 centimeters exactly because that is the definition of what a meter is and a centimeter is. I can report exactly that there is 12 inches in 1 foot because that is the basis by which we measure an inch and a foot. There is no uncertainty in that because that is the definition as readily agreed on. The other way to have an exact number is something you can physically count. I can count the number of students in a room. I can count the number of markers in a bin. I can count the number of, if I take the time, the number of jelly beans in a dish. That will take a lot longer and it'll be a lot harder to do, but it is possible. However, if I were to try to approximate, the number is no longer exact. Now, the other type of number is an uncertain number, one that is not exact, whether by approximation or by the accuracy of our measuring tools. Anything that is measured scientifically will have some degree of inexactness. We are not robots, and even robots have certain tolerances which they are been programmed to allow. You can cut, unless you can cut something down to a micron distance, you're not going to be exact on a cut. You can get close, but depending on how easily you can measure it, depends on how accurately you can report the number. So when you have uncertainty, it distracts from how well you can report a number. And this uncertainty leads to certain things such as inaccuracy in numbers or inaccuracy in precision. Some of these things will throw off your measurements. Your accuracy itself will determine how close to the actual answer it is, because even though you maybe get the wrong answer, there is a right answer out there. The only way to really check that is to compare it based on standards. So if I know exactly how much sugar I mixed into this water, there is a set concentration of sugar. However, if there's a way to test for that, you can still get it wrong if you don't measure it properly. So there's things that can throw that off. Now, precision is how consistent a set of values are to each other. How repeatable. If you do a sample 3 times, 4 times, 5 times, how often do you get numbers that are the same or in the same degree of accuracy? So you might see it like, oh, you got a bunch of numbers clumped up except for a couple outliers. Those outliers are destroying your precision. Sometimes people in statistics will use t-tests or various other tests to dispose of outliers because they throw off the exactness of your numbers. They throw off how to what degree you can report your numbers. But for the most part, we need to consider those valid numbers. So the best way to imagine this is standard deviation. Now there's various sources of why these errors can occur. Some of them are your fault, some of them are not. Sometimes it's just natural human fallacy. Sometimes it's the machine or instrument you're using. Sometimes it's just the measurement device. You cannot measure more accurately than your measurement device. So if I use the markings on a graduated cylinder that has markings every 20 milliliters, and I have a graduated cylinder that has markings every 1 milliliter, the 20 milliliters will not give me an accurate number within the ones digit, while the 1 milliliter one will give me an accurate measurement within the ones digit. However, it will not give me a very accurate measurement within the tenths or hundredths digits, so we would need an even more accurate graduated cylinder to measure that. But so this degree of uncertainty leads us to significant figures that we need to consider. So depending on your book, you might call it a significant digit or significant figure. The digit just reflects the placement of the number and the accuracy of to which it's measured. So we're saying, how well do we know this number? How well do we know this number? These two pieces of glassware can measure, well, one can measure up to 250, one can measure up to 500, but if you look at the exactness, the one glassware measures at the 100, 150, 200, 250, every 50 mils. And even then, it's not going to be super exact. The other guy looks like 10 units between every 50. It measures down from essentially 25 mils to 250 with 5 mil increments. So we can measure up 5 mil increments a lot more accurately than I could measure in the other one. Now, when I use my calculator, if I divide 1 divided by 7, I'm going to get a long string of numbers. Some of these are artifacts that will be generated by the mathematical operation. And will not truly be known. They are not, just because your calculator punches out a number does not mean it is measured with the correct degree of exactness. If I take 1 gram and I divide it by 7 milliliters, my density would not be the whole number. I would want to round this to the proper significant digits, to the numbers we know with some degree of certainty. So now we have to trust some things, but when we read off a number from a piece of paper, or we measure something from a ruler, every non-zero number must be considered significant. Every non-zero number must be considered significant. The zeros are where it gets tricky. Zeros can either be significant or non-significant depending on the circumstances. So, the purpose of this is the significant zero. The purpose of a significant zero is that it tells us something about the digit when accurately measured. It tells us we know this to be 0. A non-significant zero signifies a magnitude of a crudely made measurement. So if I had tried to measure out 200 mils in both of these pieces of glassware, because this only measures every 50 mils, the beaker on the left, I would know it is 200 and it's accurate to the hundredths place, it's accurate to the tens place, but is inaccurate to the ones place. So the third digit, the second zero, would be a non-significant zero because it just tells us it's big, but we don't actually know that's 0. It could actually be 205 mils. It could be 199 mils. We don't know because the beaker does not allow that. Now, because the graduated cylinder there is accurate to the fives place, we can know that if I measure out 200, it's accurate to the hundreds place, it's accurate to the tens place, it's accurate to the ones place. But is it accurate to the tenths place, the decimal place? No. So it only reported as 200 with all the numbers being significant. So, with that in mind, there are special rules for helping to recognize a zero is significant or not, whether the number has a decimal or it doesn't have a decimal. So remember, our non-significant zeros just tell us size. Any zero to the left of a non-zero digit, for example, is not significant. So in this case, 0.003, the 2 zeros just tells us it is the 3 is known at the hundredth place, but those other 2 digits are not useful. Any zero between significant digits is always significant. So 903, the only way we can know 3 is if we know the 0 between it. If we know the hundredths place to be accurate and we know the ones place to be accurate, by proxy we must also know the tens place. Because if we don't know the tens place, we don't know the ones place. So because of that, all 3 numbers are significant. any zero to the right of any non-zero digit, as long as they have a decimal place, are considered significant. The only way to report 70.00 is if you know the ones place is accurate, the tenths place is accurate, and the hundredth place is accurate. If I did not know those to be 0 and 0, I could not report them. I would leave them off. Now, the thousandth place is unknown. We don't know whether that's big or small or exists at all, and so we don't report the number. The idea, this is where do we round the number to? Where do we round the number to? We're rounding it to the hundredth place. Now, any zeros to the right of a non-zero digit in an integer, such as 4,000, so a number without a decimal, are uncertain. If no further information is given, we must assume all zeros there are not significant. So 4,000, if I say there was approximately 4,000 fans in the stadium, that means we do not know the hundreds place, we do not know the tens place, we do not know the ones place, but we do know the thousands place rounds to 4,000. And the final thing is all digits in the coefficient of a number in scientific notation are significant. So if I report a number in scientific notation, it is assumed that all the numbers I have reported are significant, which means all are valid and known. They are exact. So just looking at this to determine this, I won't go to the I won't bother to go to the my chart, my .cam for this. Just looking at it. So the first thing you note about this number, is there a decimal? Is there a decimal? There's not a decimal. So that means all zeros that come at the end are not significant. So I know the hundreds place to be 500. I know the 10,000ths place to be 4. The 100,000ths place to be 3. The only way I can know the 5 is if I know that to be 0. So how many sig figs? I have 1, 2, 3, 4. If I were to turn this into scientific notation, it has to be a number between 1 and 10. So I'm going to write 3.405. Now, how many places would I have to move the decimal? I'd have to move it 1, 2, 3, 4, 5. So 3.405 times 10 to the 5th. Times 10 to the 5th. Now, this guy, there's 3 zeros ahead, but all those tell us is that this number is small. We don't need to report them because we know this to be small. So we have 4, we have a 5, we have a 9. Now the only way we could report this 0 behind it is if we knew that to be 0. So we're going to report 4 sig figs, and we have to move the decimal 1, 2, 3 to the right. So it's going to be 4.590 times 10 to the negative 3rd. And 304, 3.3 and 0/4 is going to be 3 sig figs, and to turn that into scientific notation, we just multiply by 10 to the 0th because we do not move the decimal. So if you have a decimal, it's from the first number on back. If we don't have a decimal, it's the last number to the left. Now, why do we really need to consider this? Because we're going to be doing math with these numbers. And depending on the math, it's going to depend on what degree of accuracy can we report a number. If you take a very inexact number and you mix it in with a very exact number, we do not gain more knowledge, we lose knowledge. So when we add or subtract or multiply and divide with varying degrees of uncertainty, we're going to lose some of our significant digits. And all that means is we will round them away. They don't get truly lost, but the exactness is lost, and so we have to round it until we know what we can reliably report. So when we add or subtract numbers, we look to the position and the location of the last significant figure. And we'll always keep the lesser position. So you're going to line these up based on their decimals. Based on the decimals of the full number. Don't leave them into scientific notation. You have to convert them out. But you're going to line them up based on their places. And you're going to add them together. If there is no significant digit in one of those places, that placement will be rounded away. So in the case of 3.40 and we're adding 0.054, yes, your calculator will give you 3.454. However, what's not known is that 340, who knows what that other place is? And because we don't know what that other place is, it could be higher and it could be lower. And so we cannot report that anymore. We cannot report that anymore because we don't know it anymore. And so all we can do is round that away. So we report only what we know. I mean, it's counterintuitive for our human brains. If I weigh about 200 pounds, and that's not true at all, but if I weigh about 200 pounds and I eat 1 pound of food, what's my new weight? Your brain says I should be 201. But I could be a little bit higher than 200. I could be a little bit lower than 200. I could be a lot higher. And so to say, I know it's 201 is a lie. I just know it's still about 200. It's not big enough of a change to matter. Now, this example, 4,200 liters. If I subtract out 342 liters, the math says it should be 3858. But it could be higher than 4,200. It could be lower than 4,200. We don't know. And so all we know is that it rounds to 3,900 with some degree of accuracy. Now when we multiply or divide, we have to keep the number of significant digits rather than the place. So if I'm multiplying to find the area of a area carpet I'm going to need, if I have 45 meters, which is 2 sig figs, and 104 meters, which is 3 sig figs, even though the calculator punches out 4680, I know I need about a 4,700 meter squared rug, because we cannot reliably say it's going to be 4680 because the inaccuracy measured in the first measurement. However, if I know it's a 45.3 meter rug, 45.3 and 104, suddenly it's now, I can say the number is 4711.2, and that rounds to 4710. I know I need a slightly bigger rug because of that. All because of that 0.3 that we maybe ignored before. So we'll finish this off with these calculations. So we have 4.43. We're going to add it to 3.294. grams and grams. So we have 3.25 grams over mils, and we're going to multiply it by 0.35 mils. And this one is a hard one because it's a two-step. How would we go about doing that? So order of operations, we'll look at that in just a second. Okay, with that in mind, we'll jump to that. Okay. So, when we add and subtract, we line them up. So 4.43, 3.294. So when we add these together, we keep that carry the 1, so that goes to 7.724, rounds to, we can only report 7.72 grams, because this could be higher than 3, could be lower than 3. We don't know, we just know it rounds to 3. Now, 3.25 times 0.35, just a simple multiplication, gives you 1.1375. However, this is known to 3 places. This is only known to 2 places, so I can only report that it's 1.1 grams. I only know it's about 1.1 grams. That's the only degree of accuracy I can know for certain, because the volume could be greater or less than, and we don't know. It's so small it's hard to measure. Now this one, so PEMDAS, parentheses, exponentials, M, multiplication, division, addition, subtraction. So let's do my parentheses first. So 35.04 minus 31.4. So that cancels out. It becomes 4, but I have to, so 4, 10, so 3.64. Now you can round it here, or you can round it later. The number will not change by much or at all, depending. Let's go ahead and round it here, 3.6. Now if I divide that by 1.404, 2 sig figs, 4 sig figs, we can only know 2 of those numbers, even though my calculator punches out a big slew of numbers. So my answer is only 2.6. 2.6, because we have to round to the second digit, because we only know that to 2 significant digits. Now with that in mind, let's just show the answers. That's where we will stop. We'll look more about the math aspect of this in another video, where we'll look at dimensional analysis.